So today the plan is to introduce you to Quartus, how to use Quartus or how to write Verilog code in Quartus to model the digital circuit that we have learned uh, in the previous class, and we will learn how to verify the circuit and the design to see whether it works based on the specification or not, right? By writing the test code, or what we call the test bench, and do the simulation and see when we give the output, the input to the design, and we will observe the output, okay, and see whether it is consistent with our specification. For example, consistent with the truth table or not. Okay, so let's look at what we have again last week, right? So this is chapter 2. Last week we have looked at this, how to model the combinational circuit, and I think we have looked at until the adder subtractor circuit and also the comparator circuit, right? So we have learned until this. We have learned how to generate the overflow, negative, zero, and also the carry. The carry is C, one of the quiz question, right? So hopefully you can answer this, because we have discussed a lot last week. Okay, so one of the question in the quiz asks you, when we perform an 8-bit computation, right? 8-bit number add to another 8-bit number, and see whether the overflow is generated or not. What about the negative? What about the zero? And what about the carry? Okay. We have done until here last week. So today I will not go to the multiplier, but I will explain on how to use Quartus in order to design, or in order to write a Verilog code. Okay, so let's maybe design something like this. Okay, this code for the what we call the 7-segment decoder. Okay, and see how we can get the output in the simulation. Okay, so let's say if we have something like this. Yeah? So let's design a decoder, this decoder, a 7-segment decoder, where we decode this all right. In Verilog. So let's start with the Quartus. So you can run the Quartus software from your PC. Okay, the one that I shared with you is the Quartus Prime version 20.1. Okay, so you install the Quartus, so you can get this whenever you launch the Quartus, what you can get is the interface of the software like this. This is an empty interface, empty window. Okay, when you need to create what we call a project in order to create a design. Okay, so this is what we call the project navigator window. It will show you the list of projects that we have. Okay, when we create a project, uh, this is the main window, panels that we've been used to create our design. But before that, we need to create the project first. Okay, this is the message window where when we do certain operation, it will produce the messages, right? Like for example, when we compile our design, we will see the error message or warning message here. Okay, so now let's create a new design. Let's do that. Okay, so at first, when you want to create a new design, what you need to do is to create a new project. Okay, so you can use this option. We call it new project wizard. Okay, or you can get from here, file, go to new project wizard, same thing. Okay, when you click that, you will have this window. Just click next here, and this is very important for you to choose where you want to save your project. You want to keep your project, I mean the folder in your PC. So you need to create a new one, because this is a good practice. This is not like the other software, like when you use Microsoft Word, for example. You can save your file in one folder, right? But in design, in Quartus, or maybe other programming language like C, so the best practice is to have one folder for one project. Okay, you don't mix many projects, put many projects in one folder. So in this case, the best place to save your file is in your hard drive. In my case, I use the C drive. Let's say, for example, I have a folder called Quartus. This is the installation folder. It's different from the installation folder. I've been used a different folder to save my design. Okay, so I create new folder called Quartus. Let me create a new one for this design. Let's call it 7 segment decoder. Okay, this is the folder, and then we select this folder and create the project name, or the module name in our case. So the name is 7, let's call it 7 segment, like this. Click next here. Project type, so normally we use empty project. If we want to create a new project, we don't use the template. We use means that we create or build our design from zero. Okay, so choose the empty project, go to next. Add files, this is an option if you want to create a newly project or new design without using your previous design or any other IP. So this one, you just click next. But if you have other design to attach in your design, you need to attach the file here. All right, so for example, if you want to instantiate the module from the previous module, or from the IP, so you need to add that file. It will be a Verilog file as well that you need to add here. Or if you miss this tab, you can add later in the assignment window here, assignment menu here. Okay, so here you click next. The device. So the device is important if you want to implement your design in the actual hardware. I mean, in this case, is the FPGA, right? So in this case, because we just want to simulate the design, yeah. So let's say Quartus to select the device for us automatically, right? But if you want to use the actual hardware, you need to select, because we have a lot here, so we can select which is the hardware that we want to use or want to implement our design. Okay, in our case, just we're not selecting this, so we just click next. This setting also click next. So this is the summary of the this setting before we create a new project. Done means that you can click finish. So click finish here. Okay, the class is recorded so that you can I will post the recording such that you can refer to the video when you try to learn on your own. Okay, so when we have created a new project, what we will see is something like this, where you can see that at the project navigator you see the project name 7 set like this. Okay, this empty window here, gray color means empty, there is nothing yet. So whenever you want to write a Verilog code, what you need to do is to create a new Verilog file. So you go to file, click new, or you just click this shortcut. Okay, click this. So you will have a lot of design file option. Okay, so in our case where we choose Verilog HDL file, click this and click OK. So you will have the empty text editor that you will use to write your Verilog code. Okay, so now let's write code. So when you start to write your code, you can see that the color of the text, if you write like this, it is black. But if you have write the complete word module, for example, because module is a Verilog keyword, so the color will be in blue. But other than that, other than the Verilog keyword, the color will be black. So we will have another color which is red, will represent the number in Verilog. Okay, so module, in our case, the module name must be the same as this one, so we will use 7, and please remember that Verilog is case sensitive, meaning that if you use capital S, here also capital S must be exactly the same. Okay, so here let's design something like we want to design this. Okay, so we will have the input here, W, and the A, B, C, D, E, F, G. Let's combine this just like what we have there. We use A, B, C, D, E, F, G. One word for the output. Anything else? Done, right? We have only W and this for the output. Input will be 3-bit, 4-bit. Here we have W 3 to 0. We have output which is 7-bit, right? Which is this one. So I just copy this. Okay, very easy. Output, and it should be right because we will use the behavioral modeling to model this. So ABCD should be using rec data type as well. Okay, we use always block to model the circuit. Okay, and because we have a lot of option, right, like this, so it is better to use case statement instead of if and else statement. So in this case we use case statement, case W. So if W equal to, okay, here you can write in binary like this, 0 0 0 0, okay, or you can write in decimal, means 0, means that if W equal to 0, so the output of this one is equal to this value, right? So this is 7-bit, so you can have 7, and you can see the color is red color for representing a number. Okay, so it is 1 1 1 1 1 1 0, right? 1 2 3 4 5 6 7. Okay, this is for when W equals 0. So you can see that Verilog is easy if you have the truth table, because we can create that easily using case statement. Okay, for the next one you can copy this and change the value to this 0 1 1 and the rest 0. Yes, we have 1 0 here for 1 1 0, 1 1 0 1. We have 1 1 here for 0 0 1. We have 1 0 0 for 0 1 1, 0 0 1 1. This, and we have number 5 here, 1 0 1 for 1 0, and the rest 1. Is it correct? I don't think so. This one is number 5, 1 0 1 1, 1 0 1 1, 0 1 1. We have number 6, which is 1 1 0. Number 6 is 1 0, and the rest is 1. We have number 7, number 7 is 1 1 1, and we have yes, and we have number 8 or 1 0 0 0. We have all 1. Number 8 is the easiest one. We have number 9. Number 9. We have 1 1 1 1 0 here, and we have 1 here. All right, so we have only the number from 0 to 9 because the 7th segment here can only display from number 0 to number 9. All right, number 10 you need another digit, right? So but you have 4 input here, W3 to W0, so you should have other number, right, more than 9 until 15 or 1 1 1 1. Okay, but you don't have output, means that the output is don't care for the rest, for other number than this. So what we need to do is that for others, yeah, other than this, so we can use default keyword. Default means that other than this value, the output will be don't care. So this is how we write 7-bit don't care. Don't care it's X. Okay, you can write X to 7-bit or only 1X. Also the same. Okay, and then done. So you can end case here. Okay, case, you open the case statement here, and this is end case to close the statement. So this exactly representing the truth table here, right? So we can see that Verilog is very easy. When we have the truth table, okay, we can create the design very quickly using behavioral modeling with the case statement. All right, now we have the design here already, so we can now check our design whether we have any syntax error or not. Okay, to do that, what you need to do is to save the design first. Save. Okay, the name is by default is this one, the name of our module. So we need to use this one. You cannot change the name, because if you change the name, you will get an error message. Okay, just save it. And then to check the error message, we have two options. First is this one, this shortcut, or you go to processing, go to start, you select for this start analysis and elaboration, okay, or start analysis or and synthesis, okay, either one. So for at first, I recommend you to use this one because it is fast, okay, to check the design, okay, or you can use shortcut here, same thing. Okay, when you click this, you can see the process is displayed here, right? So it takes a while until you get the finish the synthesis, the analysis and elaboration. So it will show the message here, 0 errors, means that there are no errors. One warning, and this one warning is okay. It's not a concern, but if you have more than one warning, so you should check the design. Maybe your design got issues. Okay, in this case, one warning is because we use the light version or the free license. So there's one license. When we use the free license, means that we cannot use full feature of the software. So it will show the warning that, okay, when you do this, it will overloading your machine or your computer, means that all the resources of your computer will be used by the software. You cannot control it, right? But if you have a paid license, you can control this. So this is not because of the design issue, but this is actually the software that we use, and this is okay for us, yeah, to have this warning. Doesn't matter. So it looks like the design is okay for now. We need to check whether, or we need to verify the design whether it is correct based on our specification or not. In our case, we need to see that the output of this design, when we give the input like this, it is exactly this, and is it consistent with the truth table here that we have here. So to do that, you need to write a test code. Okay, the test code is called testbench in design, in the electronic design. Okay, so what is testbench? Testbench is Let me explain a testbench. What is that? So in our case, let's, for example, this is our design, and we call this design as, let me make it bigger. Call this design as 7 sec. All right, this is our design, and we have the input, which is which is W, and this W is 4-bit, where we have W 3 to 0, and we have the output called A, B, C, D, E, F, G, and this one is 7-bit, right? Is it 7-bit? Yeah, 7-bit based on this. We create a module like this, all right? And now we want to test this module or this design, whether it is correct or not, okay? So what we need to do is we need to create a new file, a new module called a test module, like this. We call this module as testbench. So we need to give the signal to the design, the input, and the input should be based on this truth table, and we will observe the output here, right? And this is of course 7-bit. This is of course 4-bit. And let's call this this module as test okay. This is the name of the test module. So what we need to do is we need to create a new module. Yeah, the big box. Create a new module where the test module will be inside this. The design will be inside the test module, right? So to do this, we need to write a new Verilog code. Yeah, a test code. This is a Verilog code as well. So you can see last week when we start to learn Verilog in chapter 1, here, so we have learned almost all of this, input, output, wire, rack, integer, not yet. We will learn in the next chapter. Okay, but here the module description part, we have learned as the assign continuous statement used for data flow modeling. We have the initial block. Yeah, this one is not introduced. Haven't introduced to you, and I said that this one is used for the simulation purpose. Okay, used in simulation code. So we will use today this one. Yeah, the always block we have learned, the gate instantiation we have learned, and the module instantiation we also have learned. Okay, so today we will use initial block, right, to create the task code. And of course, this is a Verilog code as well. Okay, so to do that, you need to create a new Verilog file. Okay, and the module name is module. The name is this. Test 7 fact. Okay, let's use that as a name. And you need to have this bracket without the port list. Okay, because in the test we don't have the port, we will have the signal, and this signal, okay, let's call this W as well, but the signal, and this, let's call this A, B, C, D, E, F, G as well. Or you can give other name. For example, if you're not comfortable with this name, this one is too long, for example, so you can have like, for example, W in this is DEC. Okay, just that. But one thing to note, to notice is that the declaration for this signal is not, because this is not a port, so you cannot declare this as port. You need to declare as rack for the input of your testbench, and this you need to declare as wire for the output of your test code. All right. And one more thing is that when we want to do simulation, what we want to do is actually we want to simulate our design relative to time. Okay, so it will be something like this. When we do simulation, we will have a timing diagram to view how your signal change, for example, from 0 to 1 or 1 to 0. Like, for example, if we have the gate like this, A, B, F, so we will have A, B, F, and we will look at the signal, the transition of the signal based on the time. Like, for example, if our time is each view in 10 nanosecond, means that the next will be 20, 30 nanosecond, 40 nanosecond, and so on. So, for example, at first, for A, we have logic 0, B logic 0, so F will also be 0, right, for AND gate. But for example, here we have A equal to 1 at 10 nanosecond, and B still 0, and of course F still 0. And let's change this to this, and F still 0 at 30 nanosecond, from 20 to 30 nanosecond. But if we have both 1 like this, so F will go to 1. So we will view the signal like this in simulation in terms of the timing diagram. Okay, so you can see that we use the time, or the simulation is relative to time, means that the time is is very important in simulation. So we need to have or declare the time. So to do that, before we create the module here, what you need to do is that you need to create what we call the time scale. Okay, so the keyword for time scale is you need to have this time scale keyword, and you need to use this symbol. This symbol is called is this one. Okay, if you look at your keyboard, you can see that this is the symbol. Okay, so you need to put this first. Yeah, you can see that, or it is very small. Maybe I can zoom this so that you can see. This, see, you need to put this symbol before you write time scale. And the time scale, you need to specify two time parameter. One is the first one, and this is the second one. I like to use 1 nanosecond / 1 nanosecond. What does this mean? This means that the first one is called the time unit. Yeah. So let's me explain about this time scale or time declaration in the test code. All right, when I write like this, time scale 1 nanosecond, 1 nanosecond. So the first 1 nanosecond representing what we call the time unit, and the second one is called the time precision. So what is time unit? Time unit is this. When we write timing in Verilog later on, we will not writing like this to write 1 nanosecond or 10 nanosecond or whatever time you want to put in Verilog. We cannot use just a number like this, okay? Or we cannot use 10 nanosecond or 10 second. No. So Verilog will not understand this. So what we will do is that we will use the hash symbol and followed by number to represent time. So hash 10 means that this is 10 time unit. So when we declare time unit as 1 nanosecond, so this means that the time this represent is 10 nanosecond. It's meant by 10 multiplied 1 nanosecond, which is 10 nanosecond. Right? If you write this 10 nanosecond for time unit, 10 here, when you write 10 here, it means that 10 multiplied by 10 nanosecond. So this is equal to 100 nanosecond. See? So this time unit is multiplied by what you write here to create the actual time that you want. Okay, in this case, when you write 10, it is multiplied by 10, so you have 100 nanosecond. Okay, if you write 1 nanosecond, then you will get exactly 10 nanosecond here. Okay, so in the code, I write 1 nanosecond means that my time unit is 1 nanosecond per unit. This is time precision, the second one. Time precision representing the resolution of the simulation. I mean, in the simulation, for example, if we have again time like this is 0 second. All right. So when we have the input AB, the output will be plotted. Okay, so the software will plot the output based on the calculation. Yeah, it will be the algorithm to calculate what is the value of B, what is value of A, right, to produce F. Okay, but how frequent is that calculation is performed by the software? The answer is based on the time precision that we use. So if we write 1 nanosecond time precision, meaning that the software, yeah, the simulation software, which is the ModelSim that we use, we evaluate the output, okay, read the input and evaluate the output every 1 nanosecond. Means that if we have time 0 to 10 nanosecond, so the output will be plotted every 1 nanosecond. 1 nanosecond is your system will evaluate the output and plot. 2 nanosecond, and again 3, and again every 1 nanosecond. All right. If you write it, yeah, the precision is 10 nanosecond, means that the output is plotted every 10 nanosecond. Right. So in our case, we use 1 nanosecond time unit and 1 nanosecond precision. I mean that it is quite resolution is quite high. Okay, is it good? Now let's go back to this. Now we want to create this module. Yeah, I mean the big one. So in the normal design, in the circuit design, like this one, when we design this, so we need to declare the input and output. Okay, but for testbench, we don't have input and output. We have this one and this one. Yeah, the signal that we want to put to, yeah, send to this port. Okay, so that's signal. This signal that we want to send to the input is called the need to be declared as rack. So we declare this as rack, and the size should be the same as W. So let's call this W in, and the output must be declared as wire, and of course the size is 7-bit. We call it DEC here, DEC or DEC out, whatever you want to call it. In my case, I use DEC. Now we have declaration, and we want to have this in this testbench, right? So how to do that? Just like what we learned last week when we instantiate a module in a new module. Same as this one, we need to instantiate or call this module in our new module. Okay, so to call that, we need to call this one, right? This one. So we write the module that we want to test, and let's call this new the instantiate module as DUT, or design and test. DUT is stand for design under test, or you can use CUT, circuit under test, or whatever you want to call it. In my case, I call DUT. Now I want to make a connection between this and this, just like what we have learned last week. So this is dot W is connected to WIN, and this one is dot A, B, C, D, E, F, G is connected to DEC, connected to this, right? And this is done. So we have created this. Now after we create this, we need to put, yeah, the signal, the test signal or test signal, test value to the design. This. Okay. So how to use that? Now we need to use the initial block. So this initial block, we need to have a begin, because we will have a lot of statement here. For example, we want to at win here, we want to put this, okay, until this. So you can have at when, this is very important, because remember that in simulation we need to specify the time, at what time we want this win to be 0, for example, or bit 0. So at what time? At 0 second, right? We start at 0 second. So to write that 0 second is like this. Yeah, just like I explained here. This is 0, represents 0 second. Okay, so at 0 second we want the input to be 0, and the next 10 second, this is the next 10 second, we want the input to be 0, 1, the next one, right? And then the next 10 second means that at 20 nanosecond, this is at 0 second, if I can comment this. So this is at 0 second. This is at 10 second, nanosecond. And when you write this, yeah, after this, and the time will be add to this actually. So this is representing time at 20 nanosecond, means that this 10 add to this. So you get 20 nanosecond. So at at 20 nanosecond, we want the input to be this. So another 10 second, or at 30 nanosecond, we want the input to be this. And let's finish this. We have number 3, number 4 here, number 5 here, six, 7, 8, 9. Okay, this will be the last. Let's test for number 10 what happened, because we specify number code if 10 input is more than 9, like for example 10 10 10, the output should be don't care, right? And let's spend another 10 nanosecond before we stop the simulation. So this is how we stop the simulation. Yeah, stop. All right, and means that we end this initial block and module. Okay, so this is our test code, right? Give the input to our design, and where is our design? This is our design. This is exactly based on this thing. Okay, now we save the design, the test code. So the test code we need to save using this name. Save it. Okay, use this name. Save. All right. So we save already. Now we can check again whether we have any syntax error or not. Click this. So it will run again. Here you can see the percentage is here, and the time, how long this take, about 16 seconds. So the time here will depend on your computer speed. Okay, if your computer is good, fast, so you can the compilation process is faster than this. Okay, so it depend on your computer. So it's good, 0 errors, 1 warning. Now we want to do simulation. Okay, to do simulation, what you need to do is you need to run the ModelSim software. There are 2 options. One is you run ModelSim. Okay, ModelSim here, standalone, means that you run separately. But by doing this, what you need to do is you need to create a new ModelSim project, attach your test code and also your design code here. Means that you need to create a separate project. But the good thing is that you can run the ModelSim straight away from your Quartus without the need to create a new project. Okay, so to do that, what you need to do is you need to make sure, if you are the first time user, so what you need to do is you need to link your Quartus to the ModelSim. So this is only one time setting to link. So you go to tools, go to option. Okay, when you go to option, you go to this general and look at this EDA tool option. So by default, this one is empty. Yeah, every field here is empty. So we will use this one, ModelSim Altera, the one that we install on our PC. So this here, what you need to do is you need to find the folder, the ModelSim folder in your install Quartus folder. So what you need to do is you go to that folder. In my case, yeah, because I installed my Quartus here. So this, and the version is 20.1. So you go to ModelSim ASE here, double click this, and you browse to the, I think the last file, the last folder, Win32A LOEM, double click this, and you select this folder such that you have this path, right? Click OK, means that you tell your Quartus that my ModelSim is here. Okay, now whenever you want to simulate your design, you need to create the testbench. Actually, your testbench is the file, but you need to do some setting to tell the Quartus that, okay, you want to compile or run the testbench. Okay, so to do that, you go to assignment and go to setting. So this is must be done for every project, yeah, every new project, right? So the previous setting is only one time to link your Quartus to ModelSim, but this one you need to do for every new project. So in this case, your tool name, you go to simulation here, you go to tool name and you select the ModelSim Altera here, and by default this is none here, so we want to compile the testbench. Okay, so this is your testbench. You click this testbench, you will have a new window this. So you click new new testbench, and the testbench name should be our testbench name, right? test7sec, and the file name, you need to attach the file here. So click this 3 dot. So look at your test file. So this is the test file. Click this, click open, click add, such that the file is here. Okay, this is the your test file. Click OK here, click OK here, and OK here. Now everything is done. What you need to do is perform the simulation. So to perform the simulation, go to Tools, and you go to Run Simulation and choose the RTL simulation. Okay, again, Tools, Run Simulation, RTL simulation. Click this. So it will call or invoke the ModelSim, right? You can see here. So this is ModelSim is now running. Okay, when you click this, so this is the ModelSim window. This is still running. Okay, so if your test code is okay, so you should not get any warning or error message. Okay, like this one, this is done actually. I think in your case you will have another tab called wave, because in my case the wave window is detached. So you will see this one. So this is the output, input and output view. This is the input win, this is the output WIN, this is the output DEC, and you need to full zoom or view in one window to see the waveform. So to do that, you go to zoom full. So you can see that, yeah, this is the input and this is the output. It shows clearly. If you can zoom this, right? So you can compare the input and output with your truth table. So when 0, you have 1 1 1 1 1 0. When 1, you have this, right? So you can expand also if you want to see individual bit of this one. So this is 1 1 1 1 1 1 0, and you can see that it changed every 10 nanosecond, because in the test code we use 10 nanosecond. All right, 10 nanosecond, another 10 nanosecond. So you can see that every 10 nanosecond we can change the input to a new value, right? And yeah, this is very good. You can see that here when we have 1 0 1 0, and because in our code when it is 1 0 1 more, not in this list, yeah, 1 0 1 1 0 1 0 1 1, or what more than 9, any value more than 9, you can see that the output is don't care or undefined. In this case, you can see that x, right? Exactly. Okay, so this is how we simulate our design. Actually, you have two options to view or to simulate or to verify your design. One is the graphical view like this, where we can see the waveform, or you can view in terms of text based. Yeah, you can see here in the simulation window of this here. So what you need to do if you want to see in the text view, because sometimes text view is easier to read as compared to look at the waveform, right? So let me create this, yeah, to show you how we do that. Let's close this simulation first. Okay, we close the simulation, and let's say, for example, if we want to create the text-based simulation output, right? So to do that, you need to add one more statement. Okay, again we will use the initial block, and because only one statement is used, no need to begin and end in this case. We will use monitor command, monitor command. In this case, when we want to use to see the just like in C programming, right? When we want to print something on the screen using text base, okay, in C is printf, right? So in Verilog we use monitor command, or you can use display command, but in this case I use monitor command. What we want to see is the input W, and we want to see in binary. So how to view in binary in Verilog is %b. Yeah, if you want to view in decimal, just put %d decimal. Hexa is %h, right? So in this case, %b. Okay, and we want to see the output, which is A, B, C, D, E, F, G in binary as well. Okay, stop it, good. And this one is actually linked to WIN in our case, and this one is linked to DEC in this case WIN and DEC. Okay, with that we will create a new simulation output which is based on the text. Okay, let's check whether the syntax is correct or not. Okay, it's good. So we do simulation again. So if you use the same file, same project, so there is no setting anymore. You can run your simulation straight away. Here, click RTL simulation. Now you can run the simulation. Okay, so I think we have this already. So let's see the transcript. Yeah, we can see the text based output here. If it is small, maybe I can capture this, and let's compare with the truth table. Okay, so this is the output that we get from the simulation. Okay, and we want to compare with the one that we have here, right? Okay, so you can see here, you compare if W equals to 0, 0, 0, 0. So the output A, B, C, D, E, F, G is 1, 1, 1, 1, 1, 1, 0. Okay, so you can check if it is consistent with this, means that the design is correct. So if not consistent, means that the design is not correct, right? So you need to redesign and run the simulation again, and you can see that this one is don't care or undefined. Okay, so that is how we model the digital circuit using Verilog and do the verification through the testbench and the simulation. All right, so I think that is the tutorial today. So you can refer back to the video to learn how to use this, because by I think this week, today, now, not tomorrow, I will give you an assignment, your first assignment, where you need to design this using Verilog, Quartus. You need to write the Verilog code, and actually the code is given already. This one, yeah, this one, the Verilog code is given. This is easy, so you just design this using your Quartus, and then do the simulation and see whether your simulation you get the output like this or not. Okay, so of course this one you are not using the case statement, but you use the 2 to 4 decoder to get 3 to 8 decoder, right? But the Verilog code is given here, so you just use this, write your code here, and then do the test bench, and then see observe the output of the simulation, write your report, and then submit to author. So I will create the link in author for your first assignment. Okay, we give you 1 week to do this. Means that you need to submit after the break, the mid semester break, right? Midterm break next week. Okay, so that will be the class today, I think. Thank you. See you after the break.